Okay everyone, now let's do this question. Find the voltage across the 24 ohm resistor. Okay, so this circuit is kind of different, right? It's we have seen this kind of circuit. You call it as the Wheaton's bridge, right? This kind of circuit we usually call it as a Wheaton's bridge. And also this, you have learned the circuit one place where you have learned it. I think you have learned it as in full wave bridge rectifier, right? There instead of resistor we have diodes over here, right? So that is full wave bridge rectifier. So like that kind of resistor is this one, okay? Like that kind of circuit is this. So here they ask find the voltage across the 24 ohm resistor. So where is the 24 ohm resistor? This is the 24 ohm resistor, okay? So I will remove that resistor from here. So what will be my circuit? After removing the 24 ohm resistor, okay? What will be how will my circuit will look like? Let me see. So my circuit will become like this, that is there is a reason why I chose this circuit, okay? There's a reason why I choose this circuit, and I will tell you the reason right now. You can try to solve this question using mesh analysis and you will get the same answer, okay? You can try by solving this question using mesh analysis. You'll get the same answer. But the thing about this is that there is another way of doing this question which is much more easier. You see, since you have removed this resistor by common sense, right? You removed this resistor, so therefore there is no current through this branch, right? Which means you don't even have to draw these two lines also. That those two lines doesn't have any effect, doesn't have any meaning. Okay, but still, so there is no branch or there is no current. So therefore there is no branch at these points, right? So which means your circuit is only like this. That is one part of the circuit looks like this and the other part of the circuit looks like this. Which means what I'm trying to say is that let me draw a rough diagram. That is, one circuit looks like this. One circuit looks like this and the other circuit looks like this. The other circuit looks like this. See, because if you look over here, since no current is flowing in this branch, right? Because like we have already learned, this is an open end, right? If you remove the load, then this is an open end, so which means no current will flow through this branch, right? So therefore, which means if there is a current flowing from this battery, okay, suppose this positive terminal 220 volt is generating current I, and let that current is flowing over here. What will happen if the current is flowing? What will happen over here is that current gets split up. It gets split up into two directions, right? So let this current be I1, let this be I2. Okay, let the current in this direction is I1 and let the current in this direction is I2, right? And if I1 is flowing over here, if I1 is flowing through this 30 ohm resistor, then this I1 will not go over here. Why? Because this is an open end, right? This is an open branch. So no current will flow. The resistance is infinity. So therefore no current will flow through this branch, which means all the current that is flowing from this 30 ohm is flowing straight into the 50 ohm resistor. Which means all the current flows from 30 ohm, then it flows into the 50 ohm, then it goes back into the negative volt terminal of the battery. This is the direction of the current. What I'm talking about is this circuit. This circuit, right? I1, the current I1 flows like this, right? It goes like this, then it goes through the 30 ohm, then it goes through the 50 ohm, and then it goes into the negative terminal of the battery. This is one direction of the current. So I'm assuming the name of that current is I1. Okay. Likewise, there is another loop also. That is, if you take this part of the circuit, we have a 20 ohm and we have a 5 ohm. Right. So like I said, this total current I will get split up into two currents. This is I1, the other is I2, right? So I2 flows through this 20 ohm, and since this branch is open, no current will flow through this branch. Therefore, all of I2 will flow through the 5 ohm, right? Which means the current I2 flows through the 20 ohm, then it flows to the 5 ohm, then it goes back into the negative terminal of the battery. What I'm talking about is this circuit. Current I2, right? Current I2 flows through the 20 ohm, then it flows into the 5 ohm, then it goes back into the negative terminal of the battery. So which means all you need to do is simply write the equations of these two meshes, and you have already found the value of the current. Easily you have found the value of the current. Okay. The other process which is by applying a normal mesh analysis, but that is more time consuming. See, the reason is because totally there are 3 meshes. Actually, there's only one mesh, but the other 2 meshes are open. You see, so when you're going to, if you are going to apply straightforward, if you are going to apply mesh analysis, then you have to apply mesh current over here, mesh analysis equation. You have to apply mesh analysis equation over here, and you have to apply mesh analysis equation over here. So therefore, there are 1, 2, 3 equations. That is what will happen if you apply a straightforward mesh analysis. Okay, but this circuit has one advantage, because since no current is flowing through this branch, I can easily split up the current in such a way that those two currents will never mix each other. One current will completely flow in this direction, and the other current will completely flow, which means these two currents will never join again, right? They will only join after going into the negative terminal of the battery. So that is what is the advantage of the circuit. This shortcut method you can apply only to Wheatstone bridge. Okay, so just remember that whenever you see Wheatstone bridge, you don't have to apply mesh analysis. Okay, there is nothing wrong in applying mesh analysis. You can apply straightforward mesh analysis and you will get the same answer. Okay, but this is a shortcut method. This is the perfect method of doing it, right? An easy method. So here what I'm trying to say is that equation for I1, I'm saying this is, let this be I1. Okay, let this be I1. I1 is flowing in this direction. Okay, this is I1. Okay, and let the current in this branch be I2. Okay, which means it goes over here. This is I2. Okay, and I2. This is I2. Okay, so which means equation for I. So I can say equation for I1 and equation for I2. Because the reason is, it's not necessary to apply mesh analysis to find the Thevenin's theorem. You can apply any analysis you want. You can even apply node analysis also. The rest of all the circuits that we have done before, you can actually do those circuits. You can actually do those circuits by applying node analysis also, and you will still get the same answer. Okay. So let's do this. So equation for I1. Okay. Equation for I1. So what about I1? I1 is, if you are applying mesh analysis in this, you are applying mesh analysis over here actually, right? You are applying mesh analysis over here, which means this is 30 ohm and this is 50 ohm, which means you have is I1 into 30 plus 50 is equal to 220, right? 220. Why it is 220 is because this I1 is generating from here, right? It's coming out from here. That's why it is plus 220. So we have I1 is equal to 220 by 30 plus 50 is 80. This is the value of I1, or I1 is equal to I1 is equal to 2.75 amperes. See, in straightforward, I have already found the value of one of the current. What about I2 also? I2 is flowing in this branch, right? It is flowing in this direction, and it is also coming out from the positive terminal of 220 volts. So therefore, equation for I2 is I2 into 20 plus 5, right? 20 plus 5 is equal to 220 volt. This is I'm applying mesh analysis over here. If I apply mesh analysis over here, this is the equation I get. Or in other words, I2 is equal to 220 by 25, which is equal to, let me see, 220 divided by 25, which is equal to 8.8 amperes. See, I have already found the value of I1 and I have found the value of I2. Very easily I have found with no difficulty. This is why I'm saying you can apply this shortcut method only for Wheatstone bridge. So anywhere, wherever you see Wheatstone bridge, okay, which is a good thing. You might be scared. Don't get scared if you see Wheatstone bridge. You should actually be happy when you see Wheatstone bridge, because when you see Wheatstone bridge, then finding the current will be very easy. But one condition is that this branch must be open. This branch is open. If this branch is not open, then you have to apply the normal mesh analysis that you have done in the previous problems. Okay, but only in this case is an exception. There's an easier way of finding the current. Only if this branch is open. Okay. So now I found I1 and I2. Now I can find the value of VTH, right? So how do you want to find the VTH? You can find the value of VTH using this open mesh, or you can find the value of VTH using this open mesh. Whichever mesh you want, you can take. I will take this mesh, okay? I will find the VTH using this mesh. That is equation for VTH, okay? Equation for VTH is equal to, what is the equation for VTH? We have over here is, what is the voltage across this? It is 30 I1, right? Voltage across is 30 I1, okay, plus, let me see, 30 I1. Then what is the voltage over here? It is 20 I1, right? 20 I1. So here it is, if you are going to assume that the current is in this direction, right? Let me see. They are assuming that the current is like this, in this mesh, going in the clockwise direction, right? Or anti-clockwise, or clockwise direction. So if you are assuming that the current is flowing in the clockwise direction, then it is minus 30 I1, right? Minus 30 I1. Why? Because over here the current is flowing from the from here to here, whereas I1 is flowing from this end to this end, right? I1 is flowing from this end to this end. So the direction of the current is opposite to each other. It's the opposite to the mesh current, so it's minus 30 I1. What about over here? It is this current, this pink color current, and this I2 is flowing in the same direction, so it is plus 20 I2. Okay, and what about VTH? Is it plus VTH or minus VTH? This current is flowing from a lower potential to a higher potential, which is not what a current is supposed to do. Current is supposed to flow from a higher potential to a lower potential. So here it is flowing from a lower potential to a higher potential. So which means it is minus VTH is equal to 0. Okay. You know the value of I1, you know the value of I2, simply find the value of VTH. So here let me see, minus 30 into 2.75 plus 20 into 8.8 minus VTH is equal to 0, right? Or VTH is equal to minus 30 into 2.75 plus 20 into 8.8. Okay. Plus 20 into 8 plus 20 into 8.8, and you get this 93.5 volt. You get 93.5 volt. Okay, VTH is equal to 93.5 volt. Now I'm going to find the value of RTH, and to finding the Thevenin's resistor also, this is very easy, right? Same. But here, if you see a voltage source, right, so you have to short it. So which means your circuit will now become like this. That is, after shorting them, then we have over here and we have over here, we have over here. So this is RTH. This is the 30 ohm, 50 ohm, 30 ohm, 50 ohm. This is 20 ohm and this is 5 ohm. Okay, so now I'm going to find the equivalent resistance, right, between A and B. That is called as the RTH, Thevenin's resistor. So here, let me see, how do you want to find it? If you look over here, suppose if you look over here, these two resistors are in parallel to each other, right? Try to simplify the circuit. So these two resistors are in parallel to each other. How do I know it is parallel to each other? Because if you look at these two resistors, their endpoints are the same. That is, one endpoint is attached to terminal A, right? So one junction is exactly the same. It is connected to A. And what about the other end of the resistor? The other end of the resistor, you see this end of the resistor and this end of the resistor is one connection. It is one junction, you see, because this entire thing is shorted, right? This entire branch over here is shorted, which means this point and this point are the same. So therefore, these two resistors are actually in parallel to each other. Okay. And likewise, if you consider these two resistors, right, look at the end of the resistor. One of the end of the resistors are in terminal B, right? Both of them are connected to terminal B. So one end is the same. What about the other end? Other end also is like this, right? The other end is also like this, which means it is also shorted to each other, which means this entire junction, this entire connection, this entire junction is one junction, a single junction. So therefore, these two resistors are also parallel to each other, right? So how will your resistor? So if I'm going to combine these two resistors, these two parallel resistors, I will get 30 into 5 by 30 plus 5. And what about over here? I will get 20 into 5 by 20 plus 5. What do you get over here? Is 150, right? 150 by 35, and here you get 100 by 25, right? Here 150 by 35 is 4.286 ohms. So which means let me change the circuit. Now I have a circuit over here, A, another circuit over here that is called as B, and this is my RTH, and the one resistor over here, and that resistor is, we combine these two resistors, right? That resistor is 150 by 35, which is 4.286 ohms. Okay. And what about the other resistor? Other is 100 by 25. 100 by 25 is 4. 100 by 25 is 4. Now if you look over here, these two resistors are in series, right? Because if the same resistor, the same current flows through both the resistors, right? So therefore these two resistors are in series, which means RTH is equal to 4.286 plus 4, which is equal to 8.28 ohms, right? 8.28 ohms. Let me see if I made any mistake anywhere. Oh, I made a mistake. It is not 5 ohm, it is 50, right? It's 50. That's why I made mistake. It's a 50 ohms, not 5 ohm, it's 50 ohm over here. So which means it is supposed to be 1500 divided by 80. It is 1500 divided by 80. 1500 divided by 80. That's what it's supposed to be actually. So let me change the answer. So therefore we have 1500 divided by 80. We have is 18.75. This is actually 18.75 ohms. Okay. Let me change it. Wait. It is 18.75 ohm and this is 4 ohm, which means your answer is, let me cancel it. Your answer is 18.75 plus 4, which is equal to 22.75 ohms. Okay, this is your actual answer of RTH. Okay, I made a mistake because I have forgot to put a 0 over here to find the parallel connection between this 30 ohm and 50 ohm. I forgot to make the connection. So it is RTH is equal to 22.75 ohms. Okay, so now I can find my current through the 24 ohm resistor, which means we have a Thevenin's voltage and we have a Thevenin's resistor over here, and my load resistor is the 24 ohm, right? The 24 ohm resistor, that's this one. This resistor which I removed, the 24, I'm going to put it back to its place, so it will become like this, and this is 24 ohm, and this is, what is RTH? 22.75, right? So 22.75 ohm. And what about this voltage? VTH is 93.5 volt. This is 93.5 volt. Okay, so I find the current through that. Okay, so what is my current? I into 22.75 plus 24 is equal to 93.5, right? Kirchhoff's voltage law. So the answer is 93.5 divided by 22.75 plus 24. There, 93.5 divided by 22.75 plus 24, and you get is 2. So therefore I is equal to 2 amperes. Therefore current through this 24 ohm resistor is 2 amperes, right? This is what they asked. What is the question? Oh, the question was find the voltage across the 24 ohm resistor, right? So therefore current across the resistor is 24 ohm. Therefore voltage across the 24 ohm resistor is equal to R into I, or I into R, or I is 2 amperes into 24 ohms, which is equal to 48, right? 48 volt. Okay, 48 volt. This is the voltage across the 24 ohm resistor. Okay.